What is the first law of thermodynamics? It's not about me. It's about you. To understand the first law of thermodynamics, we need to understand three developments. The first one is the caloric theory. So this is a theory that the first law actually disproved it. Okay. The second one is the work energy theorem. This one comes straight from physics. And the third one is the famous Joule's experiments that prove the mechanical equivalence of heat. Okay, let's first talk about caloric theory. During the early 19th century, heat was thought to be an invisible, smellless fluid contained in the body. Okay, and this fluid cannot be created or destroyed. So this is something that lives inside the body. So like the system contains this fluid, and this fluid has the properties of conservation. Okay, this is not energy, and this is heat. Okay, and this quantity and the quantity of this fluid determines the temperature. So when your body has large quantity of this fluid, then high temperature, and vice versa. Okay, so in this simple view, if you have two bodies, so let's say the body on the left is high temperature, you mean that's a lot of this fluid, right? And the body on the right has low temperature, meaning it has fewer amount of this fluid. Then if you make them into thermal contact, then the fluid can be transferred from the higher temperature to the lower temperature. So and then equilibrium is established when you have equal amount of this fluid. I mean, so this is not a completely senseless theory, right? It does make sense, and a lot of famous people actually were the proponents of this theory, like Fourier and Michael Faraday, actually. So next is the work energy theorem. So this is straight from Physics 101, okay? So let's say you have a mass m, at a position right here with the velocity 1, and you apply a constant force on it until the mass is moved with the distance d, and then the mass is also accelerated to the velocity of v2. Then you can write the relationship between work and energy as follows, right? So work, which is equal to force times distance, is equal to 1/2 mv squared. So we're only assuming there's only kinetic energy, okay? mv2 squared, so the velocity, the final velocity, subtract by 1/2 mv1, which is the initial velocity, square, okay? And if you write something like this, then you can write kind of like the kinetic energy of the mass, at the end, which is Ke, which is kinetic energy, with the 2, meaning at the end state, right? Subtract by the kinetic energy of this mass at the initial state, right? Or it's just, the difference between the kinetic energy between the final and the initial state. So, I mean, this is pretty straightforward, I'm sure, for those of you who learn physics, right? And in the end, what's come out from this is that worked is you can write worked as the change in kinetic energy, or simply just work is a change of energy. Okay. So the last development is the mechanical equivalence of heat. Okay, and this is the most important to the first law of thermodynamics. Okay. So this goes into James Joule's experiment. So Joule is the units of energy. So this is important. Okay. Okay. In his experiment, he has a falling weight. Okay, attached to a paddle wheel right here, and the paddle wheel was immersed in water, and the water was contained in the adiabatic vessel. Okay, so adiabatic means that there's no heat flow from outside. Okay, so that will become important later on. Okay, so in his experiment, he proved that the falling weight, he let go of this weight, and the weight spin the paddles, right? And that action raised the temperature of water. So we know today that is because of the friction between the paddle wheel and the water, right? But in his conclusion, he stated that work of the falling weight is converted into heat of agitation of water. So agitation of water is essentially friction. Okay. So this might not sound like anything groundbreaking, but it was quite a revelation because this is a contradiction to the caloric theory. Okay. So in the caloric theory, if you want to raise the temperature of a system, you need that invisible fluid called heat to flow into the system. Okay. But in Joule's experiment, because he used the adiabatic vessel, so there's no way for that invisible fluid, if real, to flow into the water. So according to caloric theory, the water temperature should have stayed constant, right? But this is not the case, and he proved it. Okay, this is not the only experiment he did. So actually, Joule knows about or believe in mechanical equivalence of heat many years, right? But then and he has to perform many experiments until he actually can convince the people during that time. So this is not easy. This is a lot of work, right? And actually this is possible also to Joule's ability to measure temperature very precisely during that time too. So that is something quite quite incredible about the whole thing in this area. Okay, so his experiment essentially proved that work and heat is pretty much the same thing. It's equivalent, right? You can convert work into heat, right? Okay. Joules also performed a bunch of experiments to prove to show another point that you can achieve the same change in temperature of water by doing the same amount of work, regardless of the type of processes. Okay, so he even did different types of work like electrical work, electrical work, magnetic work, and he changed the I guess materials and things like that, and he still shows that if the same amount of work is applied, you get the same change of temperature of water. Okay, so and this shows that there is something called path independence in the quantity involved in this whole conversion thing. Okay, and I mean I talked about differentials before and about the property of the exact differential, and this will come into play. Okay, so how do these three developments fit into one another? Okay, so first we have the Joule experiment, and he established the mechanical equivalence of heat. Okay, so that means work and heat is equivalent. Okay. Earlier we talked about the work energy theorem, and that work can be related to the change in energy. Okay, and that was the kinetic energy, but in general, just the change in energy. Okay, you can combine that together to be heat, because work and heat is equivalent. So heat is equal to change in energy. Okay, so I just place this ... in parentheses because we don't know what this energy is, but heat is a change of something energy. Okay, all right, so back into the caloric theory, right? Heat is something inside the body. Okay, but then we just established that heat is the change of something, right? Heat is a change of energy, or heat is a change of something. Okay, so the caloric theory is not correct anymore due to Joule experiments, and instead of heat being something inside the body, heat is actually the change of something inside the body. So do you see how the heat has changed its level, meaning instead of being something, it's just the change of something inside the body, right? And from the work and energy theorem, it's the heat is the change of energy, so something energy, right? So once we have this, what do we call this something energy, right? Since if our system is moving, then we can have kinetic energy. If our system has some sort of a reference position, we can have potential energy. But we're talking about a system that doesn't really move and we don't have any reference position or anything, then so it makes more sense to call this energy something inside the body. So that's why Jules called this the internal energy, okay? And he has the letter U as a very convention for this, okay? So this internal energy also inherit properties from the two developments, you know. First, it inherit the conservation property because it is something inside the body. It's actually the property of the system. And we talked about this because, you know, there's a concept of the state variable, right? State variable is a property. So internal energy is also the property of the system, okay? And also, from Joule experiments, internal energy inherit this path, or I mean, it got the path independent property, or what a more what to be more correct would be to say that this internal energy has a differential that is path independent. Okay. So now let's look into the internal energy and more specifically the change of internal energy, okay? So we know that change in energy is work and vice versa, right? So mathematically we can write W equal to delta U. But let's see, you see this negative sign here? So this is the convention so that, you know, when the system perform work, we get the positive work. So we'll talk about this later, you know? But, you know, in this statement, work equal to change in energy, you have to kind of note that there's no heat transfer, right? Because in Joule experiment, he used adiabatic enclosure vessel, right? Since work is equivalent to heat, then you can have another scenario where you don't perform any work, right? But then you only had the heat transfer. And in that case, you can also write Q equal to delta U, okay? And we don't have any positive, we don't have the negative sign here, just the convention again, right? Okay, so we can combine these two scenarios together to have a system that can perform both work and heat, right? By having both work and heat transfer, then you can have delta U equal to Q minus W. So you just kind of combine these two effects together. And that, my friend, is the first law of thermodynamics. Mix.